Hi everybody, this is the start of chapter 10, and chapter 10 is all about circles. It's all about circles, and this chapter will take us about 3 weeks, and we should be done right before we go on spring break, and then we can all relax during spring break and be all done with chapter 10. So that's our goal. So in section 10.1, you're going to learn the vocabulary of circles and pay particular attention to tangents of circles. We're going to learn how to use the Pythagorean theorem to tell whether or not a line is a tangent to a circle and to calculate the lengths of radii and tangents. Okay, so this word tangent may sound familiar, and you heard about the function tangent of theta back in chapter 7, and these are related, okay, but we don't get into that in geometry. You'll get into it in algebra 2, and you'll find out what that relationship is and start calculating it. But for right now, all that you need to know is that the tangent that we're going to talk about today is related to that function tan of theta, which we talked a lot about in chapter 7. Okay. So the vocabulary of circles. So let's look at this little point right here. Okay. So the black lines are all the lines that we're going to be defining, and the little line the little point right here is the center of the circle. So by the center, I mean that all the points on the line of the circle are the same distance from that point, and that's what makes it a circle, okay, by definition. So let's look at another one. Let's look at some of the ones that you're familiar with. I'll change color. Okay, let's look at this guy right here. Okay, and I'm pretty sure you all are familiar with that as the diameter. Okay, and then half of the diameter is the radius, and there's a picture of the radius. So it goes from the center point to the side. And remember, I can draw the radius anywhere in the circle, and it's going to be the same length because they all are from the point, and the point is the center point is equidistant to the outside of the circle. Okay. So I'm going to erase these. Get a clean slate here. Okay. And I'll change color. Okay. So let's look at some of these others. So this guy right here. Okay. So one end of this segment is on this part of the circle, and the other end of the segment is on this part of the circle, and this is called a chord. C-H-O-R-D, chord. Okay, and this big long line here, okay, so it also touches the circle, but it keeps right on going. It's a ray, okay? Keeps right on going through the circle, unlike the chord, which stops at the circle. And this is called the secant. And when you get into algebra 2, into trig, you'll find out that there's another trigonometric function called the secant. Okay, but we won't go into that now. But you get to see what's coming. Okay, so we've got our chord and our secant. Okay, let's get another color. Okay, so this line right here, okay, it's on the outside of the circle, and it touches the circle in only one point, okay, because these lines have width. Okay, when we draw them on the computer or even with a pencil, it looks like it might touch in more than one point on the circle, but it's meant to only touch in one single very, very tiny point, okay? And this line, this is called the tangent line. And this one single point where it touches is called the point of tangency. Okay, and in the rest of section 10.1, we're going to be concentrating on this tangent line and exploring that. So here's your vocabulary. Make sure that if I give you a drawing, just like this one on the test or a quiz, that you'll be able to identify all those pieces, all those lines. It's very important. Okay. So here we have some tangents. Here's a tangent. And its point of tangency is about right there for that circle. And its point of tangency for that circle is right about there. Okay. We have another tangent. Okay. And it's tangent to this circle. And it's also tangent to this circle at their points of tangency. And then this guy, the middle line, is also a tangent. And even though it doesn't look like it, it touches both circles right at that same point. Okay? So these are called common tangents. So these three lines, this line, and this line, are all common tangents because they are tangents in common with both these circles. So this tangent here touches both circles, here and here, so it's common to those two circles, and this tangent down here touches these two circles, so it's common. And then this tangent, the green one here, touches two circles, so it's called a common tangent. Now, just note that in order to have common tangents, the circles don't need to touch. So you could have two circles that are separated. Okay, you could have a tangent that touches both, okay, at those points of tangency. Okay, and this would also be called a common tangent, okay, because it touches both circles. So they could even overlap and have common tangents. So I'll draw a picture of that. So you could have these two circles that are overlapping, and they could have a tangent, and that would also be a common tangent. Okay. So tell how many common tangents the circles have and draw them. Well, that's pretty easy because we just kind of did it. Okay. So here we have a common tangent here, and we have a common tangent here, our points of tangency. And this is just, so this has two. Okay. And here we have one. Sorry, my drawing isn't great. One there, and then just like on the last one, okay, we have a tangent between them, so there's three lines of tangency. And just like I talked about. Okay. There's also two on those, because there isn't one in the middle, because if you drew the line between the 2 points, that would be a chord, okay? And by definition, a tangent cannot go through a circle. It can only be outside of a circle, okay? So those are our common tangents. Let's get the page. There we go. Okay. So this is just a little practice. Okay, tell whether the line a line, ray, or segment is best described as a radius, a chord, a diameter, a secant, or a tangent of circle C. And this, by the way, is how you would write circle C. So that little drawing right there means circle. See, it's got the center of the circle here. And then you have a letter, or you could have a number, I guess, that talks about circles, that names it as circle C. Okay, so let's look at AC. So AC is right here. Okay, it's a segment that goes from the center of the circle to the side of the circle. So that is a radius. Okay, AB, the line AB goes all the way over from one line, from one edge to the other. So that's a diameter. And remember, the length of the diameter is 2 times the length of the radius. So hopefully you all remember that from times gone by. And DE, okay, notice DE is a ray. So from D all the way out to E, it touches the circle in one point. So that is a tangent. And then our line AE, okay, it touches the circle in 2 points, but it keeps going on either end. So this is going to be a secant. That's an A. So if I had a line that went from here to here, okay, it touched in 2 points, but it didn't keep going, okay, this would be a chord. Okay, so again, know what these are. It's very important, and it's easy points on a test just to be able to define those pieces. Okay, so we're going to have our first theorem. And remember, a theorem can be proven. We're not going to do the theorem proofs, but we're going to kind of take it on face value. But these can be proven, and actually in Geo Honors, they do a lot of these proofs. So, okay, the first part of the theorem is that a line is tangent to a circle. Okay, so this candidate would be line M, okay, if it is perpendicular to a radius. Okay, perpendicular. Okay, so here's my line. Okay, here's a radius. It goes from the center to the edge of the circle. And what this theorem tells us is that this angle right here is a right angle, so it's 90 degrees. That's going to turn out to be very powerful. Okay. Now, the converse of that is also true. If you're given a radius, let's see, let me erase this and then I'll draw it. So if you're given a radius and you're told that that radius is perpendicular to a line, any old line, that touches the circle, so you're given that it's perpendicular, okay, then you know that this guy is a tangent. So it works both ways. Okay, so if you're told that this line is a tangent, then you know it is perpendicular to a radius. Okay, if you're told that this line is perpendicular to a radius, then you know that it's a tangent. So it works both ways. Okay, let's use theorem 10.1. In the diagram, line PT is a radius of P. Okay, so we can see that, of circle P. And it says, is ST tangent to circle P? Now, it looks like it might be, but we don't know for sure. But we know by our theorem that if ST is a tangent, then this angle has to be 90 degrees. Okay, but there's no little drawing on here, except what I did, that says that it's 90 degrees. So how do we prove that this triangle here is a right angle, is a right triangle, sorry? Okay, well that's where good old Pythagoras comes in. Because remember, for a right triangle, one side a squared plus the other side squared is equal to the hypotenuse squared. And conveniently, we're given all these sides. So we can say one side is 35, so 35 squared plus 12 squared is equal to 37 squared. And we have to show whether or not that is true. So it turns out that 35 squared is 1,225. You should know 12 squared is 144. Okay, and 37 squared is 1,369. Now, is this true? Okay, pretty obviously it is. 5 and 4 is 9, 2 and 4 is 6, 2 and 1 is 3, and 1 and 0 is 1. So, yes, this is true. Okay, so, yes, line ST is tangent to circle P. Okay, so you've been given a line that's tangent, that touches a circle where the radius is, okay, and we've shown that that is a tangent, okay, because we showed that that angle, that triangle that it makes is a right angle, okay. Okay, next one. So in the diagram, B is a point of tangency. So that means where the tangent touches is that point, touches the circle is at point B. So we're going to find this radius R, okay, and it tells you it's a radius, and it tells you that it's a, this is touching the circle right here. And we know the point of tangency is on a tangent. So we know this AB is a tangent. And we know from the theorem that this must be a right angle. So again, we're going to use our Pythagorean theorem. So A squared plus B squared plus C squared. Okay, so let's take the 80 as our A, plus R squared. There's our variable. Now, now be careful. Okay, what we want is the length of this whole line. Okay, and that whole line is 50 plus R. Okay, it's not just 50, it's not just R, it's 50 plus R. So we have to square that whole thing. And you hopefully remember how to do that from Algebra 1. So 80 squared plus R squared is equal to, okay, take 50 plus R, 50 plus R. If you're in my class, this is the way that we did it. So we start with R times R is R squared, plus R times 50 is 50R. Okay, 50 times R is 50R. And we have 50 times 50, which is 2,500. So 50 plus R squared is 2,500 plus 100R plus R squared. Okay, so let's rewrite that over here. R squared plus 100R plus 2,500. Okay, so now we need to collect our like terms. So first thing we notice is that there's an r squared on both sides, so we can subtract r squared from both sides and they go away. Okay, so now we have an 80 squared, which is actually 6,400, okay, is equal to 100r plus 2,500. We subtract 2,500 from both sides. Okay. We end up with 3,900 equals to 100r. So r is equal to 39. And that's what you were asked to find. Okay. So the only really tricky part in there is that you probably haven't done a square of an expression in a while. So you need to remember how to do that. Okay, theorem 10.2, I like to call the ice cream cone theorem because the drawing for it looks like an ice cream cone. So what it says is tangent segments from a common external point, common meaning they're the same, they meet. External means it's outside of the circle, and it's a point, means it's a point, okay? And it says that tangent segments from a common external point are congruent, okay? So here's our common external point. Okay, and then we're told that these two lines are tangent. Okay, so they're going to touch the circle, okay, and they both end up at the same point, and so the theorem tells us that these two are congruent, okay, so very powerful theorem. So let's put it to work. Okay, let's use theorem point 2, the ice cream cone. Here's our ice cream cone on its side. So this says RS is tangent, oh, come on. So this is RS is tangent to circle C at S, and RT is tangent to circle C at T. So we want to find the value of x, and here's our x right here. So we know by the ice cream cone theorem, theorem 10.2, that these two lines are equal. So just like you guys are used to doing, we can set up an equation that says 3x plus 4 is equal to 28. Okay, so we're going to subtract 4 from both sides. We get 3x equals 24. X is equal to 8. Okay, so then it asks you to find the value of x. X is equal to 8, and you're done. Okay, so this is the end of the video for chapter 10, and you, after watching this, you can proceed to homework number 27, which is on paper, and you should be able to do it pretty quickly. Okay.